Constructive and destructive interference are among the most important principles in physics. They work with sound, they work with light, with other wave motions. The definition of constructive interference is where two waves meet crest to crest and trough to trough. So we'll use a crest to denote something that looks like this. It's a crest in the wave. And they meet trough to trough, and they're said to be exactly in phase and to exhibit constructive interference. Here's an example of this situation. If we denote this dotted line as a trough, so that would be like a point here, a valley in the wave, and that this is a crest, then these two speakers are oscillating, are vibrating in phase, emitting crests and troughs at the same time. So at the same time that this speaker on the right emits a trough, this speaker on the left also emits a trough. And a trough would be, in the previous language, a rarefaction, low pressure region, whereas a crest is a condensation. Okay, so what happens if we're equidistant from both of those two speakers? At this point here, that's 3 meters from either speaker. Well, at that spot, at this instant in time, the two crests have arrived at the same time because they're two solid lines. And half a cycle later, these two troughs will arrive at that spot. So if we look at the pressure as a function of time at this particular point, then the two crests arrive at the same time, and the net effect is you get double the pressure. The two pressures add together and you get twice the pressure. When the two troughs, there's two troughs that arrive at the same time, then you get a trough that's twice as deep. And so we get, that's what we call constructive interference, and it's where these two are adding together to form a louder sound. So right here at this point, the sound's going to be loud. Well, in fact, here it is. Constructive interference means that the sound is going to be loud. With the example that we did in the previous section, this is an example of constructive interference. These two crests are arriving at the same time. They add up to create a bigger crest, and then they pass right through each other. That's constructive interference. Destructive interference is where two waves meet crest to trough. So now, what you're going to do is to move this spot so it's 3 meters from one speaker and 3.5 meters from the other speaker. And we're considering here that the wavelength of these sounds is 1 meter. Distance between these two adjacent crests is 1 meter. Well, if you move this by 1/2 a meter, offset this distance to the left speaker by 1/2 a meter, you're offsetting it by 1/2 a wavelength. And in that case, then, you get a crest from the right speaker. At the same time, you get a trough from the left speaker. Well, what happens then? Here's the crest from the right speaker. Here's the trough from the left speaker. You add a positive to a negative, and you get 0. And so you add these two waves together, and you get nothing. So with destructive interference, what you're going to get is a soft sound. And that's analogous to the example we did with the slinky, where you've got a crest that's moving to the right, a trough that's moving to the left. When they overlap, they cancel each other out, and then they just pass right on through each other and continue on. So looking at this diagram, if this is one wavelength, crest-to-crest difference is one wavelength, as before, then we're going to get constructive interference here, because we've got two crests that are overlapping each other. We're also going to get constructive interference here, where two troughs overlap. Remembering that if two troughs are overlapping now, then half a cycle later, there'll be two crests there that will overlap. But at these other points, so we also, at these red dots here, we got crests overlapping, and you'll notice that this point is the symmetric point. It's equidistant from the two speakers. But we've got constructive interference also here and here. Those are not symmetric points, and the distance from one is different from the distance from the other, but we still get constructive interference. And we'll talk about what distances will give you constructive versus destructive in just a minute. We've got destructive interference at these 2 points because we've got a crest overlapping with a trough. All right, and this is the description for how you can determine whether you get constructive or destructive interference. For two wave sources vibrating in phase, state the path length differences leading to constructive and to destructive interference. So for constructive first, the path length differences are equal to m times lambda. Lambda is the wavelength. What's m? M is just an integer. It's a whole number, 0, 1, 2, 3, 4, 5, etc. And we use, as a convention, we think of L2 being the longer of the two lengths. And what are L2 and L1? L2 and L1 are the distances from the two speakers to the point of interest. So let's look first at this particular point, point A. For point A, let's call this L1, the speaker number 1, and this is speaker number 2. For point A, L1 is the distance between this speaker and this point. And that distance is 1, 2.5 wavelengths. So L1 is 2.5 wavelengths. Well, what's L2? L2 is the distance between speaker 2 and point A, which is also 2.5 wavelengths. And we're getting constructive interference. So what's L2 minus L1? Well, it's 0. And that coincides with m equals 0. So it's this equation right here. If you put in m equals 0 into this equation, the right side is just 0, and L1 equals L2, and you get constructive interference. No big deal. Let's take another example. Let's look at point B. So at this point, L1 is 1, 2.5 wavelengths. And again at point B, the distance from L2 to point B is 1, 2, 3 wavelengths. What's L1 minus L2, or L2 minus L1? Like I said, we generally take as a convention L2 bigger than L1 if they're not the same as each other. Well, L2 is 3 lambda. L1 is 2.5 lambda. What do you get? Half a wavelength. So this is the wavelength over 2, or 1/2 the wavelength. That's a case of destructive interference. L2 minus L1 is some half integer multiple of the wavelength. And in this case, for case B, m equals 0. So if m is equal to 0, we just get lambda divided by 2. And that gives destructive interference. And you said, well, I could have guessed that because this, the crest from the right speaker is meeting the trough from the left speaker. So that makes sense. The interesting thing is, though, that other values of m give you the same thing. So, for example, for constructive interference, if L2 minus L1 is equal to the wavelength, which value of m does that correspond to? Well, it's 1. 1 times the wavelength is just the wavelength. In this case, the difference between the two path lengths is 1 wavelength, and you'll still get crests meeting up with crest because you've just offset the 1 by 1 wavelength. In fact, we talked about, well, in fact, this is an example here. It's an example of that case. We've got 1, 2, 3 wavelengths from the right speaker to this point, and 1, 2 wavelengths from the left speaker. And so that would be the case where L2 minus L1 equals the wavelength, and we get constructive interference. And you can find other points as well for m, different values of m. So I think you get the idea about how that works. Let's do an example. Two in-phase speakers are separated by 3.2 meters. A listener is stationed 2.4 meters in front of speaker B. Both speakers are playing identical 214 hertz tones, and the speed of sound is 343 meters per second. Is the observed interference constructive or destructive? Well, what's relevant here in trying to determine whether we have constructive or destructive interference? And the answer is the difference in the path lengths. So if we want to call this L2 the longer of the two paths, and this one's the shorter path, L1, then what we're interested in is L2 minus L1. Well, L2 we can get from the Pythagorean theorem. We've got this side, and L2 is just the hypotenuse, which I've called L on this. And we've worked out the geometry, no big deal. It's 4 meters. What's L1? It's the distance between this speaker B and the listener, which we're told is 2.4 meters. Well, 4 minus 2.4 is our old friend 1.6. That gives a path length difference. But what matters is the difference in path lengths compared with the wavelength. And so we're going to need the wavelength in order to determine whether the interference is constructive or destructive. We're given the frequency, 214 hertz. We need the wavelength, and we know that V equals F lambda, where lambda is a wavelength, V is the speed of sound, which we're given to be 343. So the wavelength now, if we want the wavelength, we can divide both sides by F. The F's cancel. We get the wavelength as V over F. V is 343. F is 214 cycles per second, or hertz. The per seconds cancel, and we're going to get something in meters. And if you plug the numbers in, 214, half of 214 is 107. And 107 plus 214 is, I'm sorry, it's 1.6. This turns out to be, if you plug the numbers in, 1.6 meters. And, oh, there it is. I worked it out right here. So my apologies for that. But there's what we just did here. 343 over 214 is 1.6. All right, so now we've got a path length difference that's 1.6 meters. We've got a wavelength that's also 1.6 meters. So going back to this concept, are we going to get constructive interference or destructive interference? This L2 minus L1 is 1.6, and lambda is 1.6, so it actually coincides with constructive interference with m equals 1. The difference in the wavelength, difference in the paths is one wavelength, and that implies m equals 1 and constructive interference. Great. This is the pattern created by a single speaker. So you have to imagine a speaker placed in the center here and sending sounds out in all directions. It's not a, so it's an omnidirectional speaker. With two speakers separated by one wavelength, so we've got a speaker here and a speaker here that are sending out waves in all directions, with the black lines denoting crests and the dotted lines denoting troughs. Well, where do we get constructive interference and where do we get destructive interference? Well, I think you can see that here and here we get crests matching up with crests. So we're going to have constructive interference all the way along this horizontal line, as well as these two vertical lines. We'll get constructive interference everywhere there. And we'll get, let's see, destructive interference right along here. There's a dotted line that intersects, dotted line coming along like this, and a solid line coming along like that, that intersect at this point. We get destructive interference there, as well as in other locations. So if we color the constructive interference lines red and the destructive interference lines as green, that's the sort of pattern we get with two speakers separated by one wavelength. But as we continue to separate speakers more and more by two wavelengths, we get more, what we call these fringes. And constructive, destructive, constructive, destructive, constructive, etc. 10 wavelengths, we get a lot of them. I didn't even draw in the green ones. There'd be between this red line and this red line, there'd be a green one where there's destructive interference. We get a lot of patterns there. And here's an animation that shows what happens as you increase the separation. Kind of pretty, I think. Okay. So we're going to do a demo now with two speakers separated by 1 meter and a wavelength of about 0.17 meters. And so in this case, the speakers are separated by 5.8 wavelengths. So it looks something like the pattern that we showed for a 10 wavelength separation. So what I've got here is a speaker on the left, a speaker on the right. I've got a microphone and a little instrument that allows you to see what the sound level is as you move the microphone through the sound field. And basically what you're going to do is move through place where there's destructive interference, where the sound will be soft. Then moving a little bit further, you'll get into constructive interference, where the sound is loud, etc. With all of you in the same room, we could do that same demonstration and show, and you could move your head side to side and find where the sound is soft versus loud. You can't hear the two sounds coming from the two you can't hear the individual sounds from the two speakers. They're both playing the same pitch, the same tone. So what you're hearing is interference between those two sounds, depending on how far you are from the difference in distances that you are from the two speakers. Noise-canceling headphones use destructive interference. Some noise comes in to the headphones, they use these in big fighter jets, etc. Noise comes in, is detected by a microphone, and then some electronic circuitry produces a sound that's exactly out of phase, or at least approximately so, to the original noise. So that when you put the original sound together with the out of phase sound generated in the speaker inside of the headphones, then you get a reduced noise level. So there's actually a little speaker in there that combines the existing sound with the generated sound to cancel the sound. A lot of you have connected up speaker systems, home theater systems. When you attach your speaker wires, you need to make sure that the positive is going to the red and the negative is going to the black. If you do not, you can have problems that result. And here's what can happen. If, for example, we connect up this speaker incorrectly, so we switch the positive with the negative, well, then what this speaker is going to do is, when it should have been coming out, it's coming in. And so instead of this trough, it generates a crest. A trough here, crest, trough, crest, and trough. Now, at this point that we looked at before, that's the same distance from both speakers, where we would have had constructive interference, we now have a crest and a trough meeting, and we get destructive interference. So this blue curve gets replaced by the red curve, and we get cancellation at that point. So everything's just opposite. So in order to get destructive interference, if one of these speakers is out of phase, you've got to have a path length difference that's half an integer multiple of the wavelength. In this case, the path length difference is half. Well, actually, I'm sorry. You can get destructive interference for no path length difference. In this case, L1 equals L2, and because the speakers are out of phase, the interference is actually destructive. Same thing if you do the same thing, but now the path length is different by half a wavelength, and this one you connected out of phase. You got constructive, destructive, constructive, crest, trough, crest, trough, crest, trough. So now at this point, we got two troughs that are meeting. And when you have two troughs, you get constructive interference. At that point, even though the path length difference is half a wavelength. So everything's backwards if you connect these speakers out of phase. This trough becomes a crest. These two add together and you get large amplitude oscillations. This is a demonstration. If you put two speakers facing each other, and if they're in phase with each other, then this speaker moves toward the other at the they move together at the same time, and then they move away from each other at the same time. So when they're moving together in phase, they squash the air in between here, and the air squishes out, and you can hear, and then when they pull apart, the air comes back in, and we get large amount of oscillation when they're in phase. If we oscillate these instead out of phase, so this one's moving toward the other at the same time this one's moving away, so then they're going to be doing this. And as they do this, they don't push much air around. They don't squash it, they don't compress it and rarefy it like they would. And here's a demonstration of that. This is a 100 hertz sound, 100 cycles per second. That is produced with these two speakers oscillating in phase. So if you instead connect them up wrong, and you connect the red to the black, and the black to the red, with no change to the signal, then you get a much softer sound. Why is that? It's because this speaker is now out of phase with this speaker. This one moves out away from itself. At the same time, this one moves in. And so they're moving back and forth this way, and they don't push as much air around. So then back one more time to the in-phase correct arrangement